Hi, welcome to the Calculus 3 lecture series. And we are in the unit talking about multiple integrals. So it's how to do the integration for the more than one variables. Okay, so this is our lecture number 6 here. In this lecture, we're going to introduce a new coordinate system, and we call it a cylindrical coordinate systems here. And we can use this coordinate system, and maybe sometime we can simplify the integration, our triple integrations here. Okay, all right, let's take a look at our lecture notes to see what we cover on the cylindrical coordinate system. Okay, so first things here, right? Let's take a look at the cylindrical coordinate system. Have three variables is r, theta, and z here. Okay, so for any points here, so basically the cylindrical coordinate system is kind of like the combination of the polar and the Cartesians here. So that's why in here they said for any p in the space, right? So for the xy plane, you have r thetas here. Then the z is just from the z coordinate from the Cartesians here. So the cylindrical coordinate can be write as, because xy, they are the polars, right? So because xy, they are the polar, so we have the same definition as we did for the polar. X equal to the r cosine theta and y equal to the r sine theta. Then here we just say we add one more coordinate is z is equal to z here. So from the rectangular coordinate to the cylindrical is like similar like we did before for the polar. So r squared is equal to x squared plus y squared, then tangent is y over x, and then z is the z here. So it's a pretty, so this one is a kind of an easy kind of the new coordinates here, right? So basically it's a combination of the polar and the Cartesians here. Okay, so now let's take a look at how do we do this ones here, right? So in here, we say, let's try to plot the points in the cylindrical coordinates, right? So this is my polar axis. This is y, then I swing the angle. Okay, so now in here, let's take a look. Okay, so let's take a look at what we have here, right? So this one's here, right? So remember, this is the r, theta, and the what? And the z's, right? So what is this? Cylindrical is r, theta, and the z's here. Okay, so this one here is r is equal to 2. That means I'm starting here. And my theta is 0. That means I am what? I am not moving anywhere, right? So it's theta is 0. Then I'm going to go up 2 here. So this is up 2 here. Okay. So here, so this is the point, right? So here, this is how we graph it, right? So go up 2 here. So this is my point A here. Okay, now let's take a look at 3 and negative pi over 2 here. Okay, so for B's here, so I'm starting at what? I'm starting at 3. Now I'm going to swim, like the negative pi over 2, right? So we know if you go this way, this is the positive. So this way will be the negative pi over 2. Right? So the negative pi over 2, so basically this one's going to where? You're going to have come to over here, right? Okay, so it's 3, right? Then it's go down 1. Okay, so you're going down once here. So this is my B coordinate. This is my B coordinates, right? So this is where is my B going to sit, in my cylindrical coordinates here, right? Right, so this is the 3, then you swim to here, then you go down here. So this is the B. Okay, now let's take a look at C. C is 2, and so I started at 2, and then I'm going to do what? I'm going to swim pi over 4, right? So in here, I said pi over 4. So I'm swim here. So 2, I'm going to swim to here, right? Okay, then I'm go up 3, right? So I go up 3. So this angles here is pi over 4. Then I go up 3 here. So let's be careful here. So let me see here. And where is my, okay. So do a little bit, okay, so let me see here. All right. Okay, so let me go ahead and get an eraser here. Okay, so here, like we said here, this is 2. So I go down 2 and then go up 3, right? So go up 3 because this is the up 3 here. So for this point here, this is my C point here, right? Okay, so now let's take a look at the last ones here. The last one is 4. Then it's pi over 3 here. So 1, 2, 3, 4. Then I go, whoops, swim all the way to the pi over 3. So I swim to here, then go up what? Go up 5, right? So I go up 5 here, right? So this distance is 5. So this point here, this is my point D here, right? So that's how do we graph in the cylindrical coordinates here. Okay, so now the next things here, let's take a look. This is just like very mechanical. Make sure we know how to change back and forth. So if I have the rectangular is 2 and the 2 square roots of 3 and the 6. So how do I change to the cylindrical? So I know this is rectangular. So what is this? This is X, this is Y, this is Z, right? So just by the polar, I know R squared is equal to the X squared plus what? Plus Y squares here. So this is what is 16. So what is my R? R is equal to what? R equal to 4 here, right? Now I also know the tangent theta is equal to the Y over X. So Y here is 2 the square root of the 3 over 2. So it's the square root of the 3. So what is my angle theta here? My angle theta here is pi over 3 here. Then the Z will just be itself. So when I change it to the cylindrical here, so R, so it's 4, theta, pi over 3, then the last coordinate is 6, right? Okay. All right. So now let's go the backward. So if I have a cylindrical coordinate is 4, pi over 4, 3, then what is rectangular here? So this one here, this is R, this is theta, this is Z here. All right, so I know X here, just like a polar, we still remember what is X? X is R cosine theta. So this is 4 times cosine pi over what? Pi over 4. So what is this one here? Is 2 of the square roots of the 2. Then Y is equal to the R sine theta. So this is 4 times sine the pi over 4. So what do we have here? We have 2 of the square roots of the 2. So I have a x, y, and a what? And the z's here, right? So this is 2 square roots of the 2, 2 square roots of the 2. Now what happened to the z? Z is the same, it's 3 here. Okay. Okay, so now number 3 is here. They want us to identify what is the surface with the equations here. So let's say this is z squared, right? Is equal to the r squared plus x squared here. So, okay, so I know the r squared here, z squared is equal to the r squared, and then this one's here, if you take a look at this one, z squared is equal to really is x squared plus y squares here, right? So what is this one's here? So this will be what? Is if you go back to our previous unit, the vector space and the geometry, so you will find here, this is elliptical cone, right? And this cone is along which axis? This is along the z-axis here, okay? Okay, now let's take a look at this one. It's theta equal to pi over 3 here, right? So theta is equal to the pi over 3. So what is this one here? So if you take a look, this is my, okay, so this is my polar axis, right? Okay, so this is y and this is z here. So theta equal to the pi over 3. That means in here, I swing to here, right? So this is pi over 3. I swing to here. So in fact, what you're going to have here, right? So this is what you have, is a what? This is the planes here, right? So you have this plane here. Okay, so that's what is the, so we say the what is here, this is a plane, right? This is the plane and goes through and the z-axis, right? Okay, z-axis along the line, of what the line theta equal to pi over 3 here. Right, so it's kind of be able to see that is the planes here. Okay, so now let's take a look. How do we do? Okay, so the, for the integrations here, right? So the how do we change from the Cartesians into the cylindrical coordinates? Remember when we introduced this new coordinate system, one of the main purposes is try to simplify, right? Okay, so because we have that, so we said here, okay, so the theta is from the alpha beta, right? Then the alpha, the r is equal to, r is between the function of the thetas here, right? Then the z, remember z just the Cartesian, so it's a function of xy's here. Okay, so that's why you can change the, so that you change from the f of x, y, z, right? So when you talk about the f of x, y, z is here. So x you replace with what? R cosine theta. Y you place with R sine theta. And z will stay by itself. And then also don't forget in here we have these r's here. We have one actual r. What is this r's here? This is what we keep saying. This is Jacobians, right? Okay, so this is the Jacobian when we do the variable transformation. And pretty soon I'll be able to show you how to get this Jacobian. So right now, let's just try to kind of remember that for the polar coordinates, our Jacobians are, and for the cylindrical coordinates, because it's really a combination of polar and Cartesian, so our Jacobian is R also, right? So don't forget to take this one, see here. Okay, now let's take a look, for the 3 dimensions here. How do we do it? How do, how is the, the cylindrical coordinate can help us to do the, the integrations here. Okay, so let's say evaluate this 2dV where E is the solid between, this graph here. This is a paraboloid and 18 and the between the two paraboloid, right? One is on the top, one is on the bottoms here. Okay, so because of this one, so let's take a look where are they going to intersect, right? So we say these two paraboloid, so where they intersect here, they're going to intersect at when they equal to each other, correct? So it's a 4x squared plus 4y squared is equal to 80 minus x squared minus y squared. Then you do a little bit of simplification. So you say 5x plus 5y squared is equal to 80. So the x squared plus y squared is equal to 16. Right? So they are intersect in where? So in the circle, right? X plus y equal to 16, right? So let's is this this is there. This is where the intersect here. Okay, so now let's see here. So this regions here, right? Okay, so this regions here. So let's try to describe this. So because this is the intersections here, so we will say, so then we can change to the E. See here, the theta, because it's this whole circle, right? So theta is from 0 to 2 pi. Okay, so what is the R here? R is from 0 to where? To 4, right? Okay, so what is my Z right now? Z is between these two, right? So now I know Z is going to be less than, this is AT minus X squared minus Y squared. So this parabola is AT minus X squared minus Y squared. And the bottom parabola is 4X squared plus 4y squares, right? Okay, so now I know the Z is going to be between these two, right? So this is a 4x squared plus 4y squares here, correct? And now, because I'm changing to the cylindrical coordinates here, so I know that now I can say that here, the Z, I can change it to what? Okay, AT minus X squared minus Y squared, so it's AT minus what? Minus R squared, right? Now what is here? This is 4R squared. So I can write that one. Okay, so now finally, this is how do we change, right? So this is the Cartesian integration dV. Okay, so I'm going to say here. Okay, so this is still have a 2. This 2 is from this 2 is from what? From here, right? The function values here. So this is the 2. And then don't forget what do we need to times here? We need to times R. So what is this R? This is Jacobians, right? Okay. And then now I will be able to do the, the integration. So which one we want to integrate first? The one with variables, right? So I say dz. Right, so dz, so this is for the 4r squared to the 80 minus r squared. Now after that, I will say do dr. So what is r? From 0 to 4, so become a constant interval. That's good. And then we do d theta. So what is the theta? 0 to what? Is 2 pi's, right? So now this one become pretty easy. Okay, so like in here, now you can integrate here. So this is 0 to 2 pi, 0 to 4. So when you integrate the z, so what is the z here? You have 2r's, right? Then your z is 80 minus r squared and the 4r squared. Then dr, d theta here. Okay, so now you substitute. So this is then become a very routine, like a calculus 2 type of the integration. So you substitute 80 minus r to the z. So you will have what is 160 r, right? So you have 160 r and minus what? And minus, okay, so you put the z in here. So you have 160 r and minus 4r squared. So it's 10r to the cube, right? So after you integrate that, okay? And then this is dr d theta. Now it's pretty easy, right? So then the r's here, you will just do the integrations here. So this is z to the 2 pi, pi over 2. Then this r will just be 80r squared and the minus 5 over 2. And this is r to the what? R to the 4th, right? Then you put a 0 over 4 here, d theta here, right? So now let's take a look at what is we calculate here. This is 0 for the 2 pi. If you plug that one in, you will get what is here, 640 d theta. Okay, so now this one is super easy integration. So the final answer is 1280 pi. So that will be the volumes, solid between these two parabolas, right? So if you use a Cartesian, that would be pretty difficult to integrate. Correct, right? So because you need to integrate z is from 80 minus the z going to be from the 4x squared plus 4y squared to the 80 minus x squared. Then the x and the y, they also have the relations, right? So it's become pretty tedious. Okay, now let's take a look at another examples here, right? So we said that this one, they just want us to write the integrations here. So I have x squared plus y squared dv's here, and the E is the solid above the xy plane. So inside this sphere, x squared plus y squared plus z squared equal to 4, and the inside the cylinder, x squared plus y squared. So basically you have a cylinder, right? And the cylinder fit into this sphere, and you want to find the area inside this cylinders here. All right. Okay. So now let's take a look here. So first here, this is x squared plus y squared equal to the cylinders is here, right? So this is x squared plus y squared equal to 1. So I know this is r squared equal to 1, see here, okay? And also this sphere is x squared plus y squared plus z squared equal to 4. So I will have what? I will have r squared plus z squared is equal to what? Equal to 4, okay? Correct? Okay, so now we can integrate here, right? All right, so let's see here. So let's see how do we change here. So very interested here. So this is x squared plus y squared dv, see here, right? And in the e's here. Now let's try to do that. Okay. So let's take a look, see here. Z, I want to integrate the z. So z squared is equal to 4 minus r squared, correct? Then you take the square root. Z is equal to the positive or minus 4 minus r squared. And here we take a positive because it's above the z's, right? Okay, so this is the z's here. So I know z is from the 0 to 4 minus r squared here. And then what is the r? Because we are looking for the volumes, right? Inside this cylinders, right? Okay, so what is my r's here? R is what? R is from 0 to what? 0 to 1. Then easily, what is my theta here? Is theta is from 0 to 2 pi. Okay, so now let's try to do it here. So x squared plus y squared will become what? R squared. And don't forget, what are other things we have? This r. But again, what is this r? This is my Jacobians, right? Okay, now I'm going to do, so which one I'm doing first? dz, right? Because I want to integrate it out with variable. So dz is from 0 to what? 0 to 4 minus r squared. Now, after dz, I do the dr, so it's from 0 to 1, correct? And then d theta is 0 to what? 2 pi. So if you can just say this is 0 to 2 pi, 0 to 1, and this is 0 to 4 minus r squared. So this is r cubed, right? Now it's dz, dr, d theta, okay? So in fact, this one, the integration is pretty easy because when you have z, and so the 4 minus r squared, you put it here, you might need to use like the integrated by part a couple of times to integrate out here. Okay, so that's why I just want to ask to write it out to see how do I change from the Cartesian plane for the integration to the cylindrical. Just like the polar, right? After you change it, you find out the integration become much, much easier. Okay, instead of you have square roots, a positive and negative, and it's just will be simplified. Hopefully will simplify to the integration boundaries will be the fixed constants boundary. So that would be great, right? Okay, that's it. So this is a pretty easy sections, and so basically this new coordinate system is we are quite familiar with, right? So it's a cylindrical is like the combination of the polar. So just like we did for the other section, the polar is good if your integration region is what? If your integration region is a circular, right? So in here, it's the same thing. The reason why we call it the cylindrical, that means if your integration region is somehow, it looks like a cylinder, right? Okay, so like in this one, this is a perfect candidate for using the cylindrical coordinates. All right, that's it. And I hope that you enjoy this new coordinates and we just introduced, okay? That's it, okay? Guess we'll talk to you in our next coordinates here, okay? Bye.